What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to take a look at some more fun with orthogonal projections. Let's take a look at some important theorems for the section. We have the orthogonal decomposition theorem. It says let W be a subspace of vector space Rn. Then each vector y in Rn can be written uniquely in the form y equals y hat plus z, where y hat is a vector in subspace W, and z is in W perp, and that's a perpendicular subspace. And in fact, if the vectors u sub 1, u sub 2, so on and so forth to u sub p is any orthogonal basis of subspace W, then the projection y hat can be written in the following manner, right? That's in the span of these vectors. So y dot u sub 1 over u sub 1 dot u sub 1 times vector u sub 1 plus y dot u sub 2 divided by u sub 2 dot u sub 2 times vector u sub 2 plus so on and so forth, plus y dot u sub p divided by u sub p dotted with u sub p times vector u sub p. And this gives us that projection vector. And then, okay, so that's half of it. Y can be written as this sum. So we already have y hat as the projection. Z then is given by y minus y hat. And these two, y hat and z, are going to be orthogonal vectors. So this is our orthogonal decomposition theorem, that I can decompose this vector y into the sum of these two orthogonal vectors. Y hat is our projection onto the orthogonal basis, and z is orthogonal to y hat. And we saw this in the previous lecture, but let's just get a really quick visualization of this just to refresh our memories. Let's say we had our subspace W look something like this. So this is W, and then we have our vector y. So that's our vector y. And we'll do a dotted line to sort of show that shadow being casted. And then we get our projection. Of course we do. This is our projection, y hat. And this dotted line in blue, if I want to treat it as a vector, this is the vector z. So we see y hat and z are perpendicular. We have this nice relationship that z is equal to y minus y hat. So it's a bit, and we remember that from last time too. We talked all about this stuff. And then we have properties of orthogonal projections. If y is in W, where W is the span of these orthogonal vectors building a basis, then the projection of y onto W is y itself. So this is saying, well, what if this pink vector y is already in W, is already in the span of these orthogonal vectors? Well, then it is its own projection. Right? We could do a quick picture of what that sort of is talking about, but it's not going to be anything too exciting. So this is our subspace W. And we'll draw on our vector y in pink, but we're saying y is already in W. So then it's already its own projection. I don't have to project it into the subspace because y already lives in the subspace. So say already lives in the W. Already lives in subspace W. So then it is its own projection, right? If I computed its projection, I would maybe be a little bit disappointed to see that I did all that work just to churn that same vector back out. But maybe we don't know just by looking at it, unless we have a visualization of it, maybe we don't know. But let's take a look at some examples, of course. So we're assuming that the set of vectors u sub 1, u sub 2, u sub 3, and u sub 4 is an orthogonal basis for R, and this would be an orthogonal basis for R4. Looks like I got cut off there, so R4, since I have vectors with 4 entries, where u sub 1, u sub 2, u sub 3, and u sub 4 are given, and then I have this vector x. Now, we're not going to show that it is an orthogonal basis. That would involve looking at each of these pairwise and showing that the dot products are 0. You can certainly do that, though, right? So if you wanted to actually check this, we're assuming it, you could check it by showing that every possible pairwise combination of dot products gives us 0. But so under that assumption, and it is true, if you checked it, you would be pleasantly surprised. It is true. So then now I have 4 linearly independent vectors in R4, and this gives me a complete basis for R4, which means that any other vector in vector space R4, I'm looking at you, vector x, can be expressed as a linear combination of these basis vectors. What's even better about that, since these are orthogonal vectors and not just any type of basis, it's an orthogonal basis for R4, I already know how the linear combination is going to look. I don't have to build an augmented system and solve. I can tell you how it's going to be built right away. And that means x is going to be equal to, this is a linear combination then of these vectors, u sub 1 through u sub 4. It's going to be x dotted with u sub 1 over u sub 1 dotted with u sub 1 times vector u sub 1 plus, then next it's going to be x dotted with u sub 2 divided by u sub 2 dotted with u sub 2 times vector u sub 2 plus, guess what the next piece is going to be? X dotted with u sub 3 divided by u sub 3 dotted with u sub 3 times vector u sub 3 plus, can you guess what that last piece is going to look like? What do you think? Let me know in the comment section below what you think. X dotted with u sub 4 divided by u sub 4 dotted with u sub 4, scroll down here a bit, times vector u sub 4. And this is how I can express this vector x in terms of these basis vectors that are orthogonal. Now, I skipped over the question, but I wanted to do this part first to write out this linear combination first, so now we can talk about this. So we want to write x as the sum of two vectors, where one vector is in the span of u1, u2, and u3, and the other vector is in the span of u4. Now, you could do this sort of the fast way or the slower way, and either is fine. You could actually build this entire description here. But let me show you a bit of a trick. So I want one of these parts to be in the span of u1, u2, and u3. That would be this chunk here. This is in the span of vectors u1, u2, and u3. It's just some coefficient times u1 plus some coefficient times u2 plus some coefficient times u3. So this piece is the piece that is in the span of u1, u2, u3. Well, okay, what about the other part? Well, the other part should be in the span of u sub 4. Well, that's this piece. This is just some coefficient times vector u sub 4. This is the piece that is in the span just of vector u sub 4. So I can sort of partition it this way. And now, since I want to find these two pieces, now here's where the trick is going to come into play. I could build it very directly, but what I'm going to do is I'm going to actually start with this second part. It says, well, sum of two vectors, one of them is in the span of u1, u2, and u3. The other is in the span of u4. Let me start with the other then. Let me build this one. So the piece that's in the span of u sub 4 is going to be x dotted with u sub 4 divided by u sub 4 dotted with u sub 4 times vector u sub 4. I'm just going to build the coefficient out first. So let's do x dotted with u sub 4. So that's 5 times 10 gives me 50. And then it was negative 3 times negative 8 gives me 24. Right? And then negative 1 times 2 gives me negative 2. And then 1 times 0 gives me 0. And then divided by u sub 4 dotted with itself. So 5 times 5 gives me 25. Negative 3 times negative 3 gives me positive 9. We got negative 1 times negative 1 is 1. And 1 times 1 gives me 1. Oops, a little stray mark there, which I'm going to clean up because you are worth the cleanup. Now, I'm going to go ahead and clean up this coefficient. So let's go ahead and see what we have on top. So we'd say, okay, 24 minus 2 is going to give me 22. 50 plus 22 is going to give me 72. Divided by, here I have 25. 9 and 1 is 10, so that's 35. Plus 1 is 36. Times vector u sub 4. And if I clean up that coefficient, 72 divided by 36, you know, that's really 2 times vector u sub 4. Let me actually build this. Let me bring vector u sub 4 back into play. Vector u sub 4 was 5, negative 3, negative 1, 1. And I can go ahead and find this vector. So just multiply in. I'll say, okay, 2 times 5 gives me 10. 2 times negative 3 gives me negative 6. 2 times negative 1 gives me negative 2. And 2 times 1 gives me 2. So this is the piece that's in the span of u sub 4. So we'll say the part that is in the span of u sub 4 is this vector right here. 10, negative 6, negative 2, and then positive 2. But I want to find the other part as well. So I have this part sort of underlined in pink, but I want the other part that's in the span of u1, u2, and u3. Now I can build this directly. Get a lot of practice with dot products. Feels very, honest. I can actually see what the linear combination looks like. But if all I want is that other sort of addend vector, there's a much faster way to do this. If I take x and subtract away this part, x dot u sub 4 over u sub 4 dot u sub 4 times u sub 4, that's going to solve for this part in blue. Right? So what we're saying is, if I want to solve for this part in blue, well, this is just going to be equal to x minus this piece, if that makes sense. Think of it sort of like x is equal to, I know there's sort of 3 parts here. But if I just think about that stuff in blue as just one piece, we'll say, well, that's sort of A, and then plus that part in pink. And that is just sort of one term, so we'll just see it as one term. If I want to solve for this whole piece together, these 3 pieces together all as one thing, well, I could just go back to I won't color code this, I'll go back to the yellow. We could just do, okay, so then x minus b is equal to that part A. It's really sort of the idea. So I'm going to say, take x, subtract away that piece. So what we're saying is the part that is in the span of u sub 1, u sub 2, and u sub 3 is given by x minus x dot u sub 4 over u sub 4 dotted with u sub 4 times u sub 4. And this is the faster way to do it. You can do it that longer way if this makes you uncomfortable. You're going to get the same thing. So it's kind of up to you. But let's do it the fast way. We need vector x again, and then minus the piece that's in the span of u sub 4, which I just found that was this vector 10, negative 6, negative 2, 2. Then what was x? What was vector x? 10, negative 8, 2, 0. If I do this subtraction, let's do the subtraction. 10 minus 10 gives me 0. Negative 8 minus negative 6, so that's addition. Negative 8 plus 6 gives me negative 2. 2 minus negative 2, so that's 2 plus 2 gives me 4. And then 0 minus 2 gives me negative 2. So we'll say, okay, the part that is in the span of u sub 1, u sub 2, and u sub 3 is this vector here, 0, negative 2, positive 4, negative 2. And now like I said, you could find this by building the linear combination, getting the practice with the dot products. It's going to give you the same thing. But now we have x as the sum of these 2 vectors, so let's go ahead and write it as a sum. So then x is equal to the sum of 2 vectors. One vector is in the span of u1, u2, and u3. I found that last. It was the first part it was asked for. And then the other was in the span just of U4. That was 10, -6, -2, 2. And there we have a representation for our vector x. Let's take a look at another example. Verify that u sub 1 and u sub 2 as a set is an orthogonal set, and then find the orthogonal projection of y onto the span of u1 and u2. Now we'll just do this sort of up here in the margin. If I find the dot product u sub 1 dotted with u sub 2, 1 times -1 gives me -1, plus 1 times 1 gives me 1, plus 0 times 0 gives me 0, and it gives me 0. So u1 and u2 build an orthogonal basis for a subspace of R3. They give me an orthogonal basis for a subspace of R3. So then if I want to find my projection of this vector y onto the span of u1 and u2, I can build that. That's y hat, and that's going to be given by y dotted with u sub 1 over u sub 1 dotted with u sub 1 times vector u sub 1 plus y dotted with u sub 2 divided by u sub 2 dotted with u sub 2 times vector u sub 2. And let's go ahead and find these coefficients. So that's going to be, what's y dotted with u sub 1? Well, -1 times 1 gives me -1. 4 times 1 gives me 4. 3 times 0 gives me 0. Divided by u sub 1 dotted with itself, 1 times 1 gives me 1. Plus 1 times 1 gives me 1. Plus 0 times 0 gives me 0, and then times vector u sub 1. Plus, next I want y dotted with u sub 2, so -1 times -1 gives me +1. Yeah. 4 times 1 gives me 4, sort of jumping across the vectors there. And then 3 times 0 gives me 0, divided by u sub 2 dotted with itself. So think -1 times -1 gives me +1, plus 1 times 1 gives me 1, plus 0 times 0 gives me 0, and then times vector u sub 2. Now let's go ahead and find the coefficients. So here for this first coefficient, 4 plus -1 gives me 3 over 2 times vector u sub 1, and I'm going to introduce vector u sub 1 into the game. And then here, 4 plus 1 gives me 5 over 1 plus 1 gives me 2 times vector u sub 2. So let's fill those vectors in now that we're ready for them. U sub 1 was the vector 1, 1, 0. U sub 2 was the vector -1, 1, 0. We should have the rest of the arithmetic to go through to find this projection. So, okay, what do we get here? Well, here I get the vector 3 halves, 3 halves, 0. Plus here I have the vector -5 halves, +5 halves, 0. Let's see what we get here. So 3 halves minus 5 halves is -2 over 2, which is -1. 3 halves plus 5 halves is 8 over 2. 8 over 2 is 4. And 0 plus 0 gives me 0. So this is my projection. It's my projection y hat. Now, there's something actually kind of interesting to notice about this. And if you've seen Calc 3, or you like thinking of things in 3 dimensions, I think there's a lot of intuitive sense I can make here. This vector that we got, -1, 4, 0, as our projection, looks kind of similar to the original vector y, -1, 4, 3, but we got -1, 4, 0. Look at how these vectors u sub 1 and u sub 2 are created. Notice I don't have a complete basis for R3, but I do have a basis, an orthogonal basis, for a two-dimensional subspace of R3. But notice that the third component in each of these vectors is 0. So to project this vector into the plane generated by u1 and u2, the fastest way to get it in there is just to zero out that last component. So you can sort of think about it in terms of a visual sense. And if you're used to Calc 3, you might be saying something like, okay, so the z component is 0. So I'm really just projecting into the xy plane in 3 space. If you haven't seen Calc 3, then ignore what I said. It's not really important. And we computed this directly anyways, so we don't necessarily have to marvel at it after the fact, but I think it's good to do so. I think it's good to look at it and say, well, hey, there's something kind of cool happening here. My projection is -1, 4, 0, because I'm really projecting onto this basis that's really only leaving me with those first 2 entries, and it's zeroing out that third entry. Because if I think about the span of these vectors, if I span these vectors, any linear combination is always going to give me 0 for that third entry, right? C sub 1 times U sub 1 plus C sub 2 times U sub 2. It doesn't matter how those scalar weights look. The third entry is always going to be 0 because any number times 0 plus any number times 0 is always going to give me 0. So we're just projecting into that plane. Let me know if you think that's cool. Let me know if you think it's not cool. If you say, hey, don't talk about projecting things in a Calc 3 sense. Let me know if you like that, if you don't like that. I think you should like it. I think it's great. I hope you like it. But let's do the same for another example. Here I have a new set of vectors U sub 1 and U sub 2, and let's just make sure that they are orthogonal. That's what we want. 3 times 1 gives me 3. Negative 1 times negative 1 gives me positive 1. And 2 times negative 2 gives me negative 4. You better believe it. That's 0 for the dot product. So this is an orthogonal basis. Let's find the projection then of y, which is y hat. It's the projection of y onto the subspace generated by the span of vectors u1 and u2, and that's going to be given by y dotted with u sub 1. I'm going to write it out again. I think you should too, because it helps you remember the formulas, builds the muscle memory, helps you consolidate. But we did this before, so let's do it again. So something times u sub 1 plus something times u sub 2. Let's find out what those coefficients look like. Y dotted with u sub 1, negative 1 times 3 gives me negative 3. 2 times negative 1 gives me negative 2. And 6 times 2 gives me 12. Divided by u sub 1 dotted with itself, 3 times 3 gives me 9. Negative 1 times negative 1 gives me positive 1. And 2 times 2 gives me 4. Let's do y dotted with u sub 2 next. So negative 1 times 1 gives me negative 1. 2 times negative 1 gives me negative 2. And 6 times negative 2 gives me negative 12. Divided by u sub 2 dotted with itself, 1 times 1 is 1. Plus negative 1 times negative 1 is 1. Plus negative 2 times negative 2 gives me 4. Let's see what this gives me. So y hat is equal to, let's see here, so I have 12 minus 2 gives me 10, minus 3 gives me 7, over 9 plus 1 is 10, plus 4 is 14, times u sub 1, plus, then here I have negative 12 minus 2 is negative 14, minus 1 is negative 15, over 4 plus 1 gives me 6 times u sub 2. And we can simplify these and bring the vectors back in. So 7 over 14 is 1/2 vector u sub 1. And I'll do minus here, plus a negative is subtraction really. And 15 over 6 I can reduce by 3. 3 goes into 15 5 times. 3 goes into 6 twice. Times vector u sub 2. Let's bring those vectors back in. U sub 1 was 3, negative 1, 2. There they are. 3, negative 1, 2. U sub 2 is 1, negative 1, negative 2. Yes. Perfect. More arithmetic to do. Let's do it. We have to. We want to. Bring in the coefficients. 3 times 1/2 is 3/2. Negative 1 times 1/2 is negative 1/2. 1/2 times 2 is 1. Now, I'm not too crazy. I'm going to bring the 5/2 in. I'm going to bring the negative in with it. Let me know in the comment section below when we get to 5,000 likes on the video if you prefer to subtract and just bring in the 5/2, or if you're like me, you want to add these vectors, you want to bring in the negative 5/2. Let me know if you're team subtract or team add. I'm going to be adding. Let's bring the negative 5/2 in. Does it matter? No. Just be careful. I'm going to switch this to plus, and let's bring in the negative 5/2. So that's negative 5/2. And we flip the sign because we get positive 5/2. And then negative times negative is positive. 5/2 times 2 is 5. Now I can just add the entries. I'm curious what you prefer. 3/2 plus a negative 5/2 is negative 2 over 2, which is negative 1. Negative 1/2 plus 5/2 gives me positive 4/2. Positive 4/2 is 2. And then 1 plus 5 gives me 6. There's something kind of cool that we can say about this one as well. I got the vector, my projection vector y hat is negative 1, 2, 6. That was the same as the original vector y. And that's what we talked about at the very beginning if I scroll back to it. all that this means is that the vector y is already in the span, it's all the way back here, is already in the span of those vectors, right? If y is already in our subset W, then when I project y into W, it's just going to give me y back out, because y is already its own projection. And that's what we just saw manifested here. Say, hey, we did all that work. You shouldn't feel bad about it. It's kind of a cool result. This just means that the vector y is already in the span of those orthogonal vectors. So if I go to project it in there, and I didn't know that, right? This is not a complete basis. So not every vector in R3 can be, chilling in there, but I can write the projection, of course. But this one is already in that span. So it is its own projection. I like it. All right. So now I want to let W be the subspace spanned by U sub 1 and U sub 2. Write y as the sum of a vector in W and a vector orthogonal to W. Well, okay, let's go ahead and let's check first. Make sure U sub 1 dotted with U sub 2 gives us 0. So here 1 times 5 gives me 5. 3 times 1 gives me 3. Negative 2 times 4 gives me negative 8. 5 and 3 is 8, minus 8 is 0. We have an orthogonal basis. Now the vector that's going to be in W is going to be in the span of U1 and U2, and that's going to be our projection. So what we're going to do, so really we can sort of spoiler alert on this, y is going to be equal to y hat plus z, where y hat is in W and z is in W perp, or that's orthogonal to W. Let's build y hat first. We know how to build a projection. We've been doing that quite a bit now. You remember that formula on top right here is going to be y dotted with U sub 1. 1 times 1 is 1. 3 times 3 is 9. 5 times negative 2 is negative 10. Divided by U sub 1 dotted with itself. So 1 times 1 is 1. Plus 3 times 3 is 9. Plus negative 2 times negative 2 is 4. And then for my next coefficients, numerator, 1 times 5, so that's y dotted with U sub 2 now. 1 times 5 is 5. Plus 3 times 1 is 3. Plus 5 times 4 is 20. Divided by U sub 2 dotted with itself. 5 times 5 is 25. Plus 1 times 1 is 1. Plus 4 times 4 is 16. Let's see if we can clean up these coefficients and then bring those vectors into play. So y hat is equal to, now here, we'll talk about this in a moment, but I get 1 plus 9 is 10, minus 10 gives me 0, divided by, and then here I have 10 and 4 is 14, U sub 1, plus, what about here? So now I have 5 and 20 is 25, and 3 is 28, and then divided by, here I have 25 and 16, so that's 41, and then 42. I'm going to add that last one in there, times U sub 2. So then y hat is going to be 0 times vector U sub 1, plus, and here I can reduce this. They're both divisible by 7. 7 goes into, so let's do it sort of over here. 7 goes into 28 4 times, and into 42 6 times. But then I can reduce this even further by 2, so I could have reduced by 14, it looks like. And that's going to give me 2/3 U sub 2. Whoops, I'm bringing the vectors back into play as well. So U sub 2, but literally vector U sub 2, I want to write that in at some point, and I said now we're going to do it. So vector U sub 1 is 1, 3, negative 2. And vector U sub 2 is 5, 1, 4. Now, okay, let's talk about it. So this first coefficient, the part that's in the span of U sub 1, the coefficient is 0. What does this mean? Well, think about it sort of computationally, think about it geometrically as well. This means that y is already perpendicular or orthogonal to U sub 1. So it makes sense then that this piece of it is going to sort of, let itself out, right? It's already orthogonal. But then I just have the remaining piece, so it does make the arithmetic maybe a bit easier because I don't really have to worry about half of it. But yeah, y and u1 were already orthogonal. Their dot product gave me 0. So this vector here is just going to be the 0 vector. Plus, here 2/3 times 5 is going to give me 10/3. 2/3 times 1 gives me 2/3. 2/3 times 4 gives me 8/3. So then y hat is this vector with entries 10/3, 2/3, 8/3. Now that's part of this. I'll give it as, I'll box it, star it. I don't want to forget it. Could never forget you. But I need this other part, z. Well, y is equal to y hat plus z. So then solving for z, z is y minus y hat. So I have to build this vector z, and vector y is 1, 3, 5. But I think, since I want y minus y hat, noticing the fractions that I have here might not be a bad idea to get a common denominator. So 1 is 3/3, 3 is 9/3, and 5 is 15/3. And this is still vector y. Get a different color here. Now I want vector z. Z is equal to y minus y hat. And vector y, same vector y, but I wrote it to, like fractions. 3/3, 9/3, 15/3, minus vector y hat, which was 10/3, 2/3, 8/3. I can do this. So, hey, if you like subtracting vectors, now is your chance. We're going to do it. 3/3 minus 10/3 is going to give me negative 7/3. 9/3 minus 2/3 is going to give me positive 7/3. And 15/3 minus 8/3 is going to give me positive 7/3. And this is vector z. I'm going to circle box this one too, and it deserves a star as well. And these are the two pieces. I just have enough room to write down at the bottom, do this in purple, that I can write y as the sum of two vectors. One vector is in subspace W, the span of vectors u1 and u2, and the other is a vector that's orthogonal to W, and that means that y is y hat plus z. So y is equal to some vector y hat plus z. Let me color code this. What was the vector y hat? 10/3, 2/3, 8/3. What about vector z? Negative 7/3, 7/3, 7/3. And if I, add these together, it is going to give me vector y back. But what's I think even cooler, is that these are orthogonal vectors. So this vector here, this is in subspace W. And this vector here, z, is orthogonal to subspace W. You'd say this is in W perp. You'd say this is in W perp. Very cool. And if you found the dot product of these two vectors, I'm not going to show it, but if you did, you'd be able to see that their dot product is 0 if you dot these two vectors together. Let's take a look at the best approximation theorem. And it sounds like it's trying to tell you that it is the best theorem, but it means that it is talking about the best approximation. So the theorem is really, really good, but the approximation is what is best. It might be the best theorem too. Let me know if you think this is the best theorem you've ever seen. I think it's definitely a front runner. Let W be a subspace of vector space Rn. Let Y be any vector in Rn. And let y hat be the orthogonal projection of y onto subspace W. Then this projection y hat is the closest point in subspace W to vector y, in the sense that the length norm or magnitude of y minus y hat is less than the length norm or magnitude of y minus z. So it's really saying that, okay, y hat is closer to y than z is to y, meaning the distance is always going to be smaller. And that's for all vectors v in subspace W distinct from the projection y hat. Now, I think this is intuitive. When we build that projection, the idea is that we're building the closest point in the subspace to that vector y, right? And either y is already its own projection, in which case there's no contest, Or if y is outside of w, then the projection is closest. It's just dropping straight down, just, you know, that shadow drop right down. But we can actually prove this. Let's see if we can prove it. And we'll get all sorts of stuff going here. So let's go ahead and start with the following. Let's say, let V be in subspace W, where V does not equal vector y hat. And we'll say, notice that y hat is in W. Since y hat is the orthogonal projection of y onto W, so I'll write that down here. Since y hat is the projection of y onto W, and V is in subspace W. Now, since y and V are both in W, sorry, y hat, I misspoke. Since y hat and V are both in subspace W, since y hat and V are both in subspace W, then their difference vector, y hat minus V, is also in subspace W. Because both of these vectors are in W already, if I find their difference, it's still in W. Now, let's get a picture here. So let's say, let's have these vectors here, and this is my subspace W. Then I have vector y, and vector y, let's say, is not in subspace W. And I'll drop down right there. And this builds my, I can now build my projection vector. This is my vector y hat, my projection vector, and it's in W. And then let's find, there's some other vector. Say this is vector v. I'm going to probably cut through a bit, but vector v. And vector v in purple and vector y hat, the projection in blue, are both in subspace W, this sort of plane that I have shown here. And then if I find their difference, y hat minus v, so I can sort of connect them. What color do I want? Doesn't matter. I guess I'll just stick with the purple. Do a dotted line, I guess. And this would be, this dotted line would be y hat minus v is in W. But there's one other sort of part that I can sort of draw in here, and let me get a different color for this. Definitely I'll use red. Is that I can also think about here the difference between y and v. I'll draw that in as a solid vector so it's not too difficult to see. So this would be y minus v. And this here is y hat minus v, and this is y minus y hat. And it builds, you can sort of see here in the picture that, okay, the distance that y hat is away from y is going to be better than the distance that y is from z, right? Sorry, v. So the difference that y hat is from y is going to be a smaller distance than here y from v. But let's talk further. Let's actually show this is true. Let me get a nice little picture of this sort of up close and personal. Let's see, I'll do the same color coding. I'll try to sort of flatten it out. This, in the pink, it was a dotted line. This is y minus y hat. And then this is the dotted line in purple. And that's going to be y hat minus v. Well, you can't really probably get the purple, kind of looks like a little too close to the pink, but sure. And then red was the last color. And then red was y minus v. Okay, so there's some things that we can say about this. We'll say notice. So we'll say notice that y minus v is equal to y minus y hat plus y hat minus v. And this is true literally. Y minus y hat plus y hat minus v. We'll say, well, negative y hat plus y hat cancels. So I'm left with y minus v is equal to y minus v. So this is true. But there's one more piece that I want to talk about. We said that this vector y hat minus v is also in W. So we'll say since y hat minus v is in W, it is orthogonal to any vector in W perp, namely y hat minus v is orthogonal to y minus y hat. So I have y hat minus v is orthogonal to y minus y hat. And I can draw in this right angle. And what's nice about this is it gives me, from this relationship that I have written up here, it gives me Pythagorean's theorem. So I'll circle this, and then I'll say, then, by Pythagorean's theorem, I have the magnitude of y minus v squared is equal to magnitude of y minus y hat squared plus the magnitude of y hat minus v squared. And we've almost finished showing it. There's one more thing that I want to talk about. At the very beginning, we said that v and y hat are not the same vector. V and y hat are different. Since v and y hat are different, that means this piece here is not 0, and it's going to be something positive, right? It's a length or a norm or a magnitude squared. So it's not 0 and positive. And notice here that we're talking about the distance that y is away from v. Well, that's going to be more than the distance that y is away from y hat, because it's equal to that plus some extra. This is the extra part. We're saying, well, hold on a second. Y hat and y must be closer, since if I'm talking about y versus v, how far away they are, well, it's that distance plus some extra distance. Okay, that's not good. So I said that this was actually supposed to be a better approximation, but it isn't. Well, so then we can say, then v is not closer to y than y hat. So y hat is the best approximation. Let's take a look at using this. So now we have a question that says, find the closest point to y in the subspace capital W spanned by v1 and v2. So with our best approximation theorem, we know that this is the projection. So the closest point to y in the subspace W spanned by v1 and v2 is going to be y hat. So we can start by saying this is y hat. Now let's check, of course, that v1 and v2 are orthogonal. If I dot them, 3 times 1 gives me 3. 1 times negative 1 gives me negative 1. Negative 1 times 1 gives me negative 1. 1 times negative 1 gives me negative 1. 3 minus 1 minus 1 minus 1 gives me 0. So then I can find this closest point to y in the subspace spanned by v1 and v2 as the projection. That's what the best approximation theorem says. It says the projection is going to give us that closest point. So that's y hat, which is equal to some coefficient on v1 plus some coefficient on vector v2. Let's build these coefficients. Y dotted with v sub 1 is up first. 3 times 3 gives me 9. 1 times 1 gives me 1. 5 times negative 1 gives me negative 5. 1 times 1 gives me 1. Divided by v1 dotted with itself. 3 times 3 gives me 9. 1 times 1 gives me 1. Negative 1 times negative 1 gives me 1, and 1 times 1 gives me 1. And then here I want y dotted with v sub 2. 3 times 1 gives me 3. 1 times negative 1 gives me negative 1. 5 times 1 gives me 5. And 1 times negative 1 gives me negative 1. Divided by v sub 2 dotted with itself. So 1 times 1 gives me 1. Negative 1 times negative 1 gives me 1. And then 1 times 1. Negative 1 times negative 1. So 1's for all of those. Let's go ahead and build this. Let's see what the coefficient's going to look like for each of these pieces. So here I have 9 and 1 is 10, minus 5 is 5, 5 and 1 gives me 6. Divided by 9 and 1 is 10, 11, 12. And then over here, 3 and 5 is 8, minus 2 gives me 6. And then 1, 1, 1, 1 gives me 4. I can reduce this now, so y hat is equal to, this is 1 half times vector v sub 1, plus 6 fourths reduces to 3 halves, vector v sub 2. And then here, let's bring those vectors back in. V sub 1 was 3, 1, negative 1, 1. And v sub 2 was 1, negative 1, 1, negative 1. And let's build this projection. So y hat, let's bring in the coefficients. 1 half times 3 is 3 halves. Then I'm going to get 1 half, negative 1 half, 1 half, plus, here I'll bring in the 3 halves. I get 3 halves, negative 3 halves, 3 halves, negative 3 halves. We'll add these together. So 3 halves plus 3 halves gives me 3 whole. 1 half minus 3 halves gives me negative 2 over 2, which is negative 1. Negative 1 half plus 3 halves gives me positive 2 over 2, which is positive 1. And 1 half minus 3 halves is negative 2 over 2 is negative 1. So this is our closest point. Our best approximation theorem guarantees this is y hat. This is that closest point. Is this vector y hat. We'll take a look at one last example. Find the best approximation to vector z by vectors of the form c1v1 plus c2v2. And it's really the same type of question, just worded a little slightly differently. But let's make sure that these are orthogonal vectors. So v1 dotted with v2. 2 times 1 is 2. Negative 1 times 1 is negative 1. Negative 3 times 0 is 0. And 1 times negative 1 is negative 1. So 2 minus 1 gives me 0. So yes, orthogonal, which means that the best approximation to z by vectors of the form c1 times vector v sub 1 plus c2 times vector v sub 2 is going to be the projection. I'm going to call this z hat, since I'm talking about z instead of y, but doesn't make a difference, right? Z hat, which is the projection of vector z onto the space dictated by v1 and v2. And that's going to be equal to some coefficient times vector v sub 1 plus some coefficient times vector v sub 2. Well, let's build these coefficients. We know how to do this. I want z dotted with v sub 1. So 3 times 2 gives me 6. Negative 7 times negative 1 gives me positive 7. 2 times negative 3 gives me negative 6. And 3 times 1 gives me 3. Divided by v sub 1 dotted with itself. 2 times 2 gives me 4. Negative 1 times negative 1 gives me positive 1. Negative 3 times negative 3 gives me positive 9. And 1 times 1 gives me 1. Then over here, I'm going to want z dotted with v sub 2. 3 times 1 is 3. Negative 7 times 1 is negative 7. 2 times 0 gives me 0. And 3 times negative 1 is negative 3. And then divided by here, 1 times 1 is 1, and then again, 0 times 0 is 0, and negative 1 times negative 1 is positive 1. Let's see what the coefficients are going to look like. So z hat is equal to, here we get 6 minus 6 is 0, and then 7 and 3 gives me 10. Divided by 9 and 1 is 10, plus 4 and 1 is 5, so 15, v sub 1, plus, and then here, 3 minus 3 is 0, plus 0 doesn't matter, so I'm left with negative 7. divided by 1 plus 1 plus 1 is 3 times vector v sub 2. Now let me clean up my coefficients a bit. So z hat is equal to, it's going to be some coefficient times vector v sub 1. And here 10 over 15, I can reduce the top and the bottom by 5. It's going to give me 2/3 vector v sub 1. And then minus 7/3, doesn't reduce, times vector v sub 2. Let's bring these vectors back into play. Vector v sub 1 was 2, negative 1, negative 3, 1. 2, negative 1, negative 3, 1. Vector v sub 2 was 1, 1, 0, negative 1. And let's find this projection. So that's going to be equal to, so here I'm going to have 2/3 times 2 is 4/3, then negative 2/3. Here the 3's are going to cancel, so negative 2, and then 2/3. And then we'll add, plus, let me bring the negative 7/3 in. Here I'm going to get negative 7/3, negative 7/3, 0, and then positive 7/3. If I add these vectors together, 4/3 minus 7/3 is negative 3/3 is negative 1. Negative 2/3 plus negative 7/3 is negative 9/3, which is negative 3. Negative 2 plus 0 is negative 2. And 7/3 plus 2/3 is going to give me 9/3, which is 3. So this is going to be my best approximation. So best approximation is this vector z hat, which we just found is the vector negative 1, negative 3, negative 2, positive 3. And that's it. Let me know what you're thinking about these orthogonal projections. Hope you're having a great day, whatever you're doing. No matter where you are, make sure that you always keep learning, keep dreaming, and follow your heart. Hey, I will see you next time. Until then, take care of yourself.